Next on the list, we are going to talk about series circuits that use multiple components. Now these get a little bit trickier, but our rules are still going to follow the same pattern. We're still going to have the same formulas that we used, like Ohm's law and Watt's law, but we're going to see a couple of different things that happen with these. So what happens is when we start looking at circuits, we're going to look at circuits that have multiple components in series with each other. So first thing we're going to do, we'll start off with our DC power supply, and we're going to come off. We've got one resistor here, we're going to come down, we've got another resistor here, we head back, we have another resistor here, and then it connects back up into our power supply. So we've got R1 here, we've got R2, and we've got R3. Now again, we are just labeling what these resistors are so we can talk about them individually. We can reference which one's going on. I'm going to have on here my V total, or V1, because I only have one power supply. We're going to start off with 15 volts. R1 is going to be 2.2 kilo ohms. R2 is going to be 1.1 kilo ohms. And R3 is going to be 3.3 kilo ohms. So now, one of the things that we have to consider is before, when we did our single resistor components, the R total was only R1. So with one resistor, the R total was equal to R1. Now in the multi-resistor circuits, we have to take into consideration what resistance total we're looking at. So when we go through here, if I'm wanting to push electrons and I'm wanting my current to flow and all that fun stuff, we go using conventional current flow. We go from the positive through R1, through R2, through R3, and when we get back here to our negative pole, that's how much resistance we've had to travel through, and that's how much is going to slow down all of the electrons. So my R total has to include a combination of all these resistances. So to push from one side all the way through, I'm going to get R1 plus R2 plus R3. One of the cool things about this is mathematically, these are the formulas we're going to use, but when we use this plus sign, that's also going to designate series when we start talking about configurations of our circuits. So we've got R1 is in series with R2, which is in series with R3. That's how we would read that using our symbols. So again, we got one current flow comes out of our source, comes up into R1, goes through R1. There's only one choice, so it goes to R2. R2 comes out, then it goes into R3, and then when we come back, we have a total amount of current that's flowing from our source. So looking from this, I have got I total coming out of the positive and coming around. It's going to make this side of my resistor positive because it's connected to the positive side. It's more positive than the other one, which makes this negative. My current then is going to flow out of that resistor, come into R2. Again, my current was flowing from the positive of my source, so this side is going to be more positive than this. That current's going to flow back around, come into R3. We're going to have a positive and negative, and then it's going to come up and go back to my source. So resistance total with all of that, following our current paths and all that fun stuff, is R1 plus R2 plus R3, meaning that this plus is also can be said as a series designator or a series symbol. So now that I have my resistance total, I can then solve for that. So my resistance total is going to be 2.2K plus 1.1K plus 3.3K. That is going to give me a grand total of 6.6 kilo ohms. All right, so now the next thing I have to do is I've got to look at what is going on with the rest of the circuit. How is this going to be split up? So what I have here is, since I have an R total, I can use R total and V total to solve for I total. So my current total is going to be my voltage total divided by resistance total. So I get 15 volts divided by 6.6 kiloohms. So when I go through and do that, 15 divided by 6.6K, that gives me a whopping 2.273 milliamps. Again, we're rounding it off to 3 decimal places. So now as I look through, I have this total current coming out. Total resistance compared to total voltage. So my current is going to be equal to 2.273 milliamps coming out of the positive, going through R1, R2, R3. Now anywhere in here, because it's a series circuit and because the rules of series circuit says that we have to have one continuous current path, no branches, no deviations. That means this current is the same as this current, that's the same as this current, that's the same as this current. So my I total is going to be the same as my current of R1, which is the same as my current of R2, which is the same as my current of R3. Now, initially, yes, when you flip this thing on for the first time, you're going to have a spike of current in between each one of these, and they're all going to kind of shoot up, and then they'll drop back off to where we are. So there will be a split second where we'll have a really huge current, or potential of having a huge current, but then what we're looking at is once everything's established and everything's turned on, what are my levels for all of the different values? All right, so now I can go through and I have these currents. Well, then I need to be able to find out what is my voltages across each one of these. So when we go through with this, we can then simply use our formulas to solve for voltages. So the voltage of R1 is equal to the current of R1 times R1's value. The voltage of R2 is going to be the current of R2 times the resistance value of R2. And the voltage of R3 is the current of R3 times R3's value. So in this series circuit, the current's the same everywhere, so that value right here is going to be the same. I total is the same as I1, I2, and R3, so all three of these are going to have the same value for those individual resistor currents. So we have 2.273 milliamps times 2.2 kiloohms. VR2 is going to be 2.2, I can write 2s, I promise, 73 milliamps times the 1.1K ohm resistor. And then VR3 is the 2.273 milliamps times our 3.3 kilo ohm resistor. So when we go through with those, my 0.02273 as a decimal times my 2200. So I'm going to get, so VR1 is equal to 5.001 volts, so round it off. I'm going to get that same 0.002273 times my 1100. So this one, my VR2, is 2.500 volts. And my VR3 value, 2273 times 3300. This one is 7.501 volts. So we'll box those in just to show we got our final answers. I would also put a box over here for my iTotal. That way I could find it easier if I'm filling out a table or a chart or anything like that. And so now I have my voltages and I have my currents through each one of those resistors. Well, now that I have a value, I want to double check my values to make sure that I'm doing this right. So one of the things that we have to check is we have to go back and remember, Kirchhoff's voltage loop. Okay, so Kirchhoff's voltage loop, our KVL, states that all voltages in a loop must equal 0. Okay, we should have 0 net. This is also can be restated as saying all voltage sources must equal all voltage drops. So to verify that, we need to be able to do a Kirchhoff's voltage loop and check to see if this matches. So to do a voltage loop, we can choose any point on the circuit. It does not matter. Let's go from right here between R1 and R2. Then we're going to go in the direction that our current is traveling. Just makes it easier. We don't have to make that decision. We just go in the direction of current. So then what I'm looking for is my voltage levels. And the voltage levels are going to be in part dictated in polarity by what happened with the current. So my Kirchhoff voltage loop, oops, I cannot write, KVL. So I'm going to start here, and I'm going to have a plus voltage of R2, which we did find over here, but we're going to just write it out in formula mode for just a second, plus the voltage of R3, because we hit the plus side first. We come through, we hit the negative of our power supply, so minus 15 volts, which is our V total. Then when we get through the power supply, we come back around, we run into a positive VR1, and we get back to our starting spot. So according to Kirchhoff, all voltages in a loop must equal 0. So all three of these resistors plus my power supply must equal 0. So then I can plug them in to double check. So VR2, so I have a plus 2.500 volts plus a VR1, which was 5.001 volts, minus our source, which was 15 volts, plus a 7.501 volt for VR3. So now if I go through and add those all together, I'm actually going to get a number just slightly higher. I get a positive 0.002. So my 2.5 plus 5.001 plus 7.501, that gives me a grand total of 15.002, and then I subtract the 15, leaving me with a plus 0.002. Now, for all intents and purposes, we know that in math, 0 does not equal the same thing as 0.002. Mathematically, this is true. They are not equal. But for what we're doing, a variance with 0.002, when we're looking at really the most significant digits is one decimal point right here, 7.5 or a 2.5, really. We're looking at a whole nother 2 decimal places afterwards of accuracy that we encountered. Now, our error came from when we rounded these values off. If we would have just truncated them, or if we would have gone to a different one, we would have seen a little bit different variance on this. Also, if we rounded this number up when we shouldn't have, there's lots of things that can be built into this. But in our world, in the electronics world, we have a 5% tolerance. So even if we were to look at this value, with our 15 volts compared to the 15.002, I mean, even if we just did that calculation, 15 volts in and 15.002 volts out, and just looked at it as a percentage, so then we're going to take this number, multiply it by 100 to turn it into a percentage. So even with this, 15 divided by 15.002, we have times 100, 99.987% accuracy. and we are allowed plus or minus 5%. So that means our answer, as long as it falls within 95% to 105% of what this actual value is, this is good. And a lot of times when we're going to be doing calculations and things like that, if I run into an instance where I am 3 decimal points off of what the answer is, I'm going to call that close enough. 99% of the time, that error that gets introduced is just because of rounding. So keep that in mind. This is my double check. Just because these are not perfectly exact, they're close enough for all intents and purposes. So it's not going to be that big of a deal for what we're doing. We want to be as accurate as we can, however, and like I said, rounding introduces error into our accuracy. It's just how it works. All right, so now we double checked it. Our Kirchhoff voltage loop comes out that we're good. 0 is essentially the same as 0.002 when we're looking at the grand scheme of things against a 15-volt supply. So we can feel pretty confident that our voltage for R1 is good, our voltage for R2 is good, our voltage for R3 is good, as well as the current is good. So now what I have to look at is one last aspect, and that's going to be the power in this system. So when I look at it, I have two things to start with. I have my power total, but I also have my power of R1. How much is resistor 1 power? What's the power being dropped across R2? And the power being dropped across R3. So I got to look at all of these guys. And that was supposed to be a comma, not a plus on these ones. So I want to look at the power for all of these. Power total, straight, easy. So power total, just like what we did anytime with a total, it's going to be voltage total times my current total. So what I get here is 15 volts times my current, which was 2.273 milliamps. When I multiply those together, I get 34.095 milliwatts. Okay, so there's total power. So this entire circuit with these 3 resistors is going to drop 34 milliwatts. So then when I'm looking at how this splits up, I have power of R1 is going to be equal to the voltage of R1 times the current of R1. The power of R2 is the voltage of R2 times the current of R2. Power of R3 is the voltage of R3 times the current of R3. So hopefully by now you can kind of see that this pattern is still following. I'm still using the exact same equations. I'm still using the exact same Ohm's law. I'm using everything that we did before. Just now I'm actually getting into the part where I'm looking at the relationships of each individual component to the other parameters. So the voltage of R1 is 5.001 volts. The current of R1 is our 2.273 milliamps. The voltage of R2 is going to be my 2.500 volts. And my current is 2.273 milliamps again. My power of R3 is the voltage of R3, so 7.501 volts times my 2.273 milliamps. All right, and now I can go through and solve each one of these individually. So 5.001 volts times my 2.273 milliamps gives me 11.367 milliwatts. Okay, my power of R2 is 2.5 volts times my 2273 milliamps, my 2.273. So then when I plug that one in, that gives me 5.683 milliwatts. And my last one is 7.501 times my 2.273 milliamps. And I get 17.050 milliwatts. So now I'm going through and I'm looking at, well, I've got 4 different answers. What's going on with this? And the answer is simple. My power total is a combination of everything that's happening in the circuit. These are just the individual options. So if I was to take my power for resistor 1, add that to the power of resistor 2, add that to the power of resistor 3, what do I get? Well, let's do it. 11.367 milliwatts plus 5.683 milliwatts. And then, let me get this off of those. We'll shift this screen over a little bit, maybe not. And then I'm going to add, I'll go down a line, my 17.050 milliwatts. So when I combine all of my outputs, all of my loads, all of my resistors, however you want to look at it, so I got 11.367, 5.683, and 17.050, that gives me a grand total of 34.100 milliwatts. So if I compare that to my total value, again, my values are slightly off, but again, that we get back to the rounding issue. So my 34.095 milliwatts is, for all practical purposes, the same as my 34.1 milliwatts. Again, we're looking at rounding issues. This is 0.005 milliwatts off. And if we're worried about 0.005 milliwatts, our tolerances might be too tight. But if we look at our difference in there, so 34.1 over the 34, sorry, I wrote this number wrong right here. This should be 34, not 39. I think I said the wrong number when I added them together. It should be the 34.095. So if we take our 34.1 and divide it by the 34.095 times 100, we come up with an answer of 100.014, meaning we are 0.015% off of what the answer should be. So in the grand scheme of things, not that big of a deal. We're close enough. And one of the scary things that people get hung up on is, oh no, I have too much leftover space, or these things aren't exactly added up, or whatever it may be. It's okay. It is just fine. Okay, so based on what we've learned now, we have a few extra rules that we have to look at with our series circuits. And what those come down to be is my current is the same everywhere. So right here is kind of one of our first rules. Current is the same everywhere in a series circuit. So the current leaving my source is the same current going through resistor 1, same current going through resistor 2, same current going through resistor 3. My voltages are going to combine together. My voltage drops, I guess I should be more specific in saying my voltage drops are going to combine together to give me my voltage input or my voltage source. And then my power across my resistors, so all the power that I'm using on each one of those are also going to add up to my total power, how everything is being used. So my power total, I can calculate it by using my total values, or solve each individual power, add them up, and there's my answer. All right, seems like a lot for dealing with just 2 components, but that's kind of the idea. It's very, very basic. It's very, very logical. we take one step, we go to another, and then we look at different options that we have and use the rules that we've established. Voltage adds, current stays the same, power adds. And then also the other one that we have is my resistance also adds together. So in my series circuit, I have one current path, resistance adds, current stays the same, voltages add together because of Kirchhoff, and then my power is going to add together. But now, what if I had an option that required multiple power sources instead of just resistors? It's the same idea, it's the same circuit. We just got to break it up into its individual components. So if I have a circuit that has multiple power supplies, I just have to look at my power supplies first to determine my totals. So in this circuit, I have one power supply over here on the left, so we're going to call this one V1. I'm going to have a resistor, R1. R1 is then going to come into a power supply with this orientation, and then we come into another resistor we'll label as R2, and this is my voltage source 2. So now when we go through and look at these, I have to be able to kind of figure out again what's going on. So now this is where, from our terminology, this is where we're looking at what we call series aiding and series opposing. So what we need to do is track out the individual current paths for each of these to determine if they're going to be working together or fighting each other. So source 1 we're going to do with red. So current is going to flow out of the positive and come around through R1, and then it's going to flow down through this direction, across R3, and back to the source. Source 2, its current is going to flow up this way from the positive, make the corner against R1, come down across across V1, back across R2, and then back this direction. So what we end up with is, if we look at the currents where they're going to cross together, all of my currents are now fighting each other. So because I have these positive source and this positive source coming together, if I looked at a series path, one single loop all the way back, V1 and V2 are fighting against each other. So because they're fighting, we call it series opposing. And in series opposing, we subtract our voltage sources and then we take the polarity of larger. So if we have 15 volts here and 5 volts here, so what this means is now my V total, because they're opposing each other, the currents are trying to flow opposite directions, is going to be my larger one, which is V1, minus my smaller one, which is V2. And so I'm going to get a total of 15 volts minus 5 volts. So my total voltage is equal to 10 volts, and V1 is going to be the winner. So if I was to simplify this circuit, I combine my sources together using series aiding or series opposing rules, and what I get is a circuit that then can be reduced to this. My V total is 10 volts following the polarity of this guy. And we're going to go through and find the same things that happen. So now I can go through, I can find my resistance total if I have values. So we'll just say R1 is 150 ohms, and we'll say R2 is 330 ohms. So then my R total is going to be R1 plus R2, because they both have one connection between the two of them. My voltage of R1 is going to be different than the voltage of R2, so that's going to be the current flowing through R1 times R1 itself. The voltage of R2 is the current flowing through R2 times its resistance itself. And then I need to solve what the currents are. So I need current of R1, but because they're in series, it's going to be the same as the current of R2, which is also going to be the same as my current total, because current total is what is coming out of my source. So current total is going to be voltage total divided by resistance total. So I have 10 volts with my R total. We haven't even solved that yet, so R total is going to be 150 plus my 330. So that's going to give me 480 ohms. So then here on my current total, I can plug that in, 480 ohms. And then when I go through and calculate that, I have 10 volts divided by my 480, and that gives me 20.833 milliamps. So there's current total, there is current of R1, current of R2. Then, using my Ohm's law rules, I know that's going to be current of R1, and I know that's going to be current of R2. So then I can come up here, and now I have everything I can solve for the individual voltages. So I'm going to take 20.833 milliamps, and I'm going to multiply that by 150 ohms. And I'm going to take my 20.833 milliamps, and I'm going to multiply that by my 330 ohms. So I get 20.833 milliamps times 150 ohms. So I get 3.125 volts. And my other resistor, R2, the 20.833 milliamps times the 330 ohm resistor, is going to give me 6.875 volts. And then, following Kirchhoff's voltage loop, R1 and R2 are in series. So it should be their individual voltage drops should equal my voltage total. And if I subtract that out, it should equal 0. So kind of the shortened version of my Kirchhoff voltage loop is I want all my drops equal to my source. So I have 3.125 plus 6.875. That is going to give me 10, and that is equal to 10. And we're well within our 5% because they do actually match on this one, so that's good. So then I can come back here and I can go, okay, what are going to be my polarities? Well, if I look at my current of my total, I'm going to have current move in this direction through R1. So this side is going to be positive, this side is going to be negative. That current's going to come down here, flow from right to left across R2, cut across back up here to the source, so which means this part where the current first impacts my component is going to be positive because we came off the positive terminal. This side is negative. So now I have my polarities, I have my current paths, I have my voltages. The only thing I really need now is my powers. So if I go through and solve for those, so my power total, my power of R1, my power of R2. So we're going to start with R2. So we're going to have the voltage of R2 times the current of R2. Sorry, R1, not R2. And then this one's going to be the voltage of R2 times the current of R2 to solve for the power of R2. Again, this is very, very important to make sure that when you're labeling things, to label them correctly. It does happen from time to time, but just make sure you're being slow and careful. So voltage of R1 times current of R1. So 3.125 volts times my 20.833 milliamps. And then on VR2 is 6.875 volts times my 20.833 milliamps. And then when I put those into my calculator, I get a total of 65.103 milliwatts for R1. And for R2, I've got the 6.875 and my current 2833. And down here I get 143.227 milliwatts. And then if I add these together, so power of R1 plus my power of R2 is going to give me my power total. So 65.103 plus my 143.227. I get a total of 208.33 milliwatts. And then I can double check that against my power total just as a calculation. So my power total, I'm going to use voltage total times current total. So 10 volts times my 20.833 milliamps. We plug that in, or we can just do it by moving the decimal because it's just by a 10. We get 208.33 milliwatts. So again, these two values that we just solved for should end up being very, very close to each other, if not exact. And if we get a little teeny bit of variation and some decimal point digits, like second or third decimal digit difference, I'm not too worried about that because, again, that just gets back into how we rounded and what we did.